Good morning, students. Myself, Vijay Shankar from ECE Department, Civil Engineering College. Today, we are going to discuss about the examples in the transmission lines 1. In the yesterday's class also, we completed some examples. We'll continue the remaining examples in this Unit 1, transmission lines 1. So after that, the cutoff frequency, the previous class, on the yesterday's class, we find the cutoff frequency 1 by the root L dash, the total inductance and the capacitance we got. Now, the next example is for a cable, it is decided to provide lumped loading. See the loadings of the three: continuous loading, patch loading, and lumped loading. Okay, the primary constants of cables are R, L, G, and C is given in terms of per kilometer. Find the new value of inductance. Already the inductance is a 1 milliamp per kilometer. Now we can find out the new inductance required to achieve distortionless condition. So distortionless means we have the formula is there. RC is equal to LG or LG is equal to RC. By what factor the inductance is required to be raised? See, the loading is nothing but including or increasing the inductance. So how much inductance is to be raised to get it is a distortionless condition. The distortionless condition RC is equal to LG. We need the L, so we can keep that is a L dash RC by the G. R is given 40 ohms per kilometer and C is given 1 micro. C is 0.05 microfarads into 10 to the power of -6 is a micro, and Z is equal to 1 micro ohms per kilometer, So in this you can substitute to get the inductance. L dash is equal to 10 power -6, 10 power -6 get cancelled. 0.05 by the 100 is up there, 40 into 5 by 100, and these also get cancelled, and 5 2's here and 2 2's. So 2 N per kilometer L dash is equal. Actually, in the primary constant L is equal to 1 millihen per kilometer. So the factor by which the inductance to be increased is L dash by the L. What is L dash? We got the 2, and L is given is a 1 micro. It's a 1 into 10 to the power of -3. You can simplify this. 2 by 10 to the power of -3 is a 2 into 10 to the power of 3, 200 factor. Okay. What it matters, students, by using the distortionless condition RC is equal to LC, we need to find here we can find that it is an inductance L dash is equal to, and by what factor the inductance is raised to be. The factor is 2000 factor, it is raised to get it is a distortionless. Okay. The next example. A transmission line with the characteristic impedance, of 50 ohms is connected to a 100 ohms resistive load. Calculate the voltage reflection coefficient at the load. Voltage reflection coefficient K is equal to, the formula is ZR minus Z0 by ZR plus Z0. ZR minus Z0 by ZR plus Z0. So given it is a characteristic impedance, nothing but the Z0 is a 50 ohms is a Z0 and is connected to a 1000 ohms resistive load. This means nothing but it is a ZR. The magnitude and its angle is a 0 degrees. So 100 minus 50, ZR 100 minus Z0 50 by 100 plus 50. So 50 by 150, 50 by 150, we get 1 by 3. So 1 by 3 is a 0.33 with an angle of 0 degrees. The reflection coefficient 0.333 with an angle of 0 degrees. Got it, my students? Okay. The next example. So this also we have a telephone transmission line 100 kilometers long as Z0 is given, alpha is given, the beta is given. At the frequency the 10 hertz, find the line is terminated in the ZR and is supplied by the generator with an EMF 10 volt RMS value, and RM is equal to 700 ohms. Calculate the values of IS, ZS, IR, ER, PS, and PR. It has so many things. Okay, so actually the Z0 is equal to, and the ZR is also given. And the reflection coefficient, we know the ZR minus Z0. And we can find out the e power gamma into L and e power minus gamma into L to substitute that values in the voltage V is equal to, okay, and ZS also. Substitute all the values, we'll get IS, VS, and IR, ER is equal to, ER means VR only, the voltage. V is equal to I into ZR. Okay, my dear students. Then, another example, a transmission line has the following parameters per kilometer. R is equal to 15 ohms and C is equal to 15 microfarads and L is equal to 1 milliHern and G is equal to 1 ohms. Find the additional inductance. Find the additional inductance to give distortionless transmission and calculate alpha and beta for this inductance added transmission line. Distortionless transmission line means RC is equal to LC1. So L dash is equal to RC. R is given the 15 and C is given the 15 to 10 to the power of microfarads, 10 to the power of minus 6, and G is 1 micromohms, and these two get cancelled, 15 into 15 to 25. L dash is equal. So additional inductance required is already the inductance is a 1 milliHern. Additionally is required is 225 minus 1 into 10 to the power of 3. It's totally the 224.99 here. Find the additional inductance to give distortionless transmission. Already the 1 is there. Totally for the distortionless transmission, it requires 225. Already 1 is given means you can subtract from 225 minus this. So 224.99 Hz, the additional inductance is required to give the distortionless transmission. Okay. And the calculate the alpha and the beta for the inductance added to the transmission. Inductance added to the transmission. What is alpha? Alpha, you know the formula is there. Alpha is not the 0. Definitely have the alpha is equal to R by 2 under root of C L dash and G by 2 under root of L by C. Okay, my dear students. So remember here the R plus G, once it is a C by L and it is L by C. Okay. And R is a 15 is a given, under root of C is a 15 microfarads, and L dash we got it is a 225. They're asking that calculate the alpha and beta for this inductance added transmission line. After adding the total value, it is a 225 for the L 1 milliHern. Okay, substitute all the values and calculate the value. Alpha is equal to 0.0387 Newton, not the Newton, sorry, here it is a Napier per kilometer. N is nothing but here the Napier. And the beta is a formula we have, the omega under root of L dash into C. Here omega is given 6.28 into the power of 3 radians per second. And we have the frequency is there. Let us find that also. And the beta is equal to the 6.283 into the power of 3 and under root of you can substitute L dash and the C. You get the 365 radians per kilometer. And similarly, the next example we have here, a transmission line has the following per unit length parameter. L is given, R, C, and G. All it is a primary constants. Calculate the propagation constant, the characteristic impedance of the line at 500 megahertz. Propagation constant means the P is equal to, and characteristic impedance Z naught. What is the P is equal to? P is equal to under root of R plus J omega L and G plus J omega C. So all it is a given the terms, and Z naught is equal to and under root of R plus J omega L and G plus J omega C. And we have the constants L is there for R and the C and the G. And with the frequency, the omega is equal to 2 pi F. F is given 2 pi into 500 megahertz into 10 to the power of 6. Using this, all the values, you can find out the propagation constant, the characteristic impedance, and also find the some parameters for lossless line. Okay, let us see here directly. You can use Z is equal to R plus J omega L. Z means P is equal to actually P is equal to Z into Y. Impedance and the admittance is a propagation constant. P is equal to. What is the impedance? R plus J omega L. R is given 5 plus J into 2 pi. Omega is nothing but the 2 pi into 500 to the power of 6 into L is given the 0.1 to the power of minus 6. You'll get with the magnitude and the angle 314.119. Okay. Otherwise, in terms of the rectangular form, 5 plus J into 314.15. Similarly, the G by substituting of G and the C to get the admittance Y. Y is in the polar form 0.9425 with an angle of 89.39. To find the characteristic impedance, Z naught is equal to under root of Z by this total R plus J omega L is a Z, G plus J omega C is a Y, impedance and admittance. And here, both the magnitudes you can divide and angle, so you can subtract 89.088 minus 89.39. So 89.39 is a greater. The negative value, you get the 0.151. And these two all can divide, and the root you can apply 18.25. Okay, my dear friends. Similarly, the gamma is equal to, or P is equal to propagation constant Y into Z or Z into Y. Got it? So here the angle values of polar form, convert the polar form into the rectangular form to get alpha and the beta. Real term is an alpha and the imaginary term is a beta. Alpha we got 0.2285 Napiers per kilometer, and beta is a 17.2069 radians per kilometer. And also they're asking that for lossless line, R is equal to G is equal to 0, then alpha is equal to 0. Why it is alpha is equal to, we have the formula is R by 2 under root of L by C plus G into G by 2 C by L is a formula we have. But for the lossless, transmission line means alpha is equal to 0 when the R and the G is both are the zeros. R is 0 means first term 0 and G 0, second term is also 0. And we have only the beta. Beta is equal to omega root LC. Beta is equal to omega root LC. L is given the 0.1 into 10 to the power of minus 6 and 300 into 10 to the power of it is a 0.61 into 10 to the power of minus 6, my students. And simplify, you'll get the beta is a 17.2. Okay, the 17.2 is the same, but when is a lossless alpha is equal to 0, but actually the value is a 0.22. You can substitute all the values, whatever they given, to get the alpha value directly. Alpha is equal to substituting of R, L, C, and G and C also. Then we'll get the same value, 0.2385. And the beta 17.2072. Approximately, it's both are the same. Okay. And Z0 is equal to, after neglecting the values of R and the G, Z0, the characteristic impedance Z0 is equal to under root of R plus J omega L and G plus J omega C. R is 0 and G is 0, then becomes of J omega get cancelled. It becomes L by C. L is given the 0.1 into 10 to the power of minus 6 and 300 into 10 to the power of minus 12. Okay. Then simplify, you get the 18.2574 with an angle of 0 degrees. Thus, for a high frequency like 500 megahertz, the line behaves almost as lossless line. So next example is, my friends, a transmission line with air as a dielectric. Has Z0 is equal to 5 ohms and phase constant 3.0 radian per meter at 10 megahertz. Means the given values are the characteristic impedance of Z0, 50 ohms, and the phase constant beta is also given, that is 3.0 radian per meter, and the frequency is given the 10 megahertz, 10 power 6 hertz, and find the inductance and the capacitance. They are saying that it is a line with air dielectric, is means nothing but a lossless. Dielectric is a lossless, means the conductivity is a 0. So the conductivity is as the conductivity is 0. So conductivity is a 0 means R and the Z both are the 0 and alpha is also 0 because it is alpha lossless transmission line. We know the Z0 is equal to the characteristic impedance under root of R plus J omega L by G plus J omega C. A transmission line with air as a dielectric and it is R is equal to 0 and G is equal to 0, alpha is equal to 0 is a lossless transmission line, and Z0 is equal to under root of L by C. Already the Z0 is given, so 50 is equal to root L by C. Okay, my dear friends. Then the beta is also given. What is a beta is equal to the formula in the lossless transmission line? Beta is equal to omega root LC. And that is equal to 2 pi f root LC. 2 pi f root LC. So from these two functions, we need to find the beta is given as 3 radians per meter. Okay. So to get the function the Z naught by the beta or Z naught by the beta is equal to, what is the Z naught? Under root of L by C whole divided by beta is equal to omega root LC. Okay, that is equal to root L by C, and this here 1 by omega into root LC. So in the denominator there is a root L is there, and root L get cancelled, and root C becomes a C, and 1 by omega C. That is the ratio between of Z naught by the beta. Z naught by the beta. Z naught by the beta is equal to 1 by omega C. We need to find the C is equal to. What is the C is equal to now? The omega into Z naught by the beta. Okay. Omega is a 2 pi F. Omega is equal to 2 pi F. C is equal to, it's a 1 by C, my dear students. Sorry. 1 by C is equal to omega C Z naught by the beta, and the C is equal to beta by omega Z naught, and they are showing here the R naught, it's Z naught only. Beta is given the 3, omega is a 2 pi F, 2 pi into F is a 10 mega, means 10 power 10 into 10 power 6, 10 into 10 power 6, and R naught is a 50. Okay, my dear students. So that is equal to 2 5s, again it is a 10, and 10 power 7, 10 power 8, and 10 power 9. Totally you get the 10 power minus 9, and value is a 0.954 into 10 power of minus 9. Okay, that is farads per meter. The C is equal to, we got 10 power minus 9 is a nano actually. They write the road that is a 954.9, means additionally it is getting a 10 power minus 3. 10 power minus 9 and 10 power minus 3 is 10 power minus 12 picofarads per meter. Okay, picofarads per meter. The capacitors we got. Another one, you have to find out the inductance. What is the inductance? Root L by C is equal to Z naught. Okay, Z naught square is equal to L by C, and CL is equal to C into Z naught square. Okay, what is the C here? We got 954.9 pico, 954.9 picofarads means minus 12, and the 50 is given for the Z naught, 50 square. Simplify this, we'll get the L is equal. Okay, L is equal to 2387.25 nano. We'll get the nano means 10 power minus 9, 10 per the meter. Okay, my dear students. But the next example, a lossy cable with R is equal to L is equal to C is equal to G is given, operates at the frequency. Find the attenuation constant. What is the attenuation constant? Alpha is equal to we have the R, L, C, and the G, means from the gamma you can find out the alpha plus I beta, that is equal to under root of R plus J omega L and G plus J omega C. to get the alpha from here. Means alpha is equal to the real term and the beta is the imaginary term. In these parameters, given the G is equal to 0, R plus J omega L and J omega C. As a G is equal to 0, it becomes of J omega C. It is also the under root is there. That is equal to under root of R. R is given the 2.25 plus J into 2 pi F. F is given the 0.5 giga 10 power 0.5. Sorry, here the 0.5 10 power 9. Okay. And plus, not the plus, L is also there. Omega, it's substitute the frequency only, the gigahertz, plus into L value is a 1.0 into 10 power of minus 6. Okay. Then multiply this total function with J. Again here the 2 pi into 0.5 gigahertz 10 power 9 and 1 into pico 10 power minus 12. Let's simplify this function. We'll get the imaginary coefficient is beta and the real is a alpha value. So alpha is equal to, they got a 1.125 into 10 to the power of minus 3 per meter. Okay, per meter. How we get in this, the function is j into j, you can multiply j square is a minus, and j is multiplied with this function. The value is a imaginary term. So whatever the value we got from multiplying these two functions, that is alpha. Okay, it is 1.125 into 10 to the power of minus 3 per meter. Got it, my dear students? Then another example, a transmission line in which no distortion is present has the following parameters. Z0 is given and alpha is given, and the velocity, the V is equal to. Determine the R, L, G, C and the wavelength at 0.1 gigahertz. So for the distortionalized condition, RC is equal to LG. RC is equal to LG. The Z0 is equal to root L by C. Z0 is equal to root L by C. Alpha value, when it is alpha value is equal to, so actually the formula is R by 2 into root L by C plus G by 2 into root C by L. Okay. Now I can substitute that value, so you'll get alpha is equal to R by Z0 under root R, that is also equal to the R under root of L by C by substituting of G is equal to this value. Z is equal to this value. Okay. Then alpha is equal to R by Z0 and R is equal to alpha into Z0. Alpha is given and Z0 is also given. To get the resistance is 1.0 ohms per meter. And L is equal to, from these only you will get L is equal to Z0 by the V. The 50 by the 0.6 into 10 to the power of 8. You know the V velocity V is always, you can multiply, that is a 3 into 10 to the power of 8 nanohen per meter. And G is equal to, we got alpha square by R from this expression only. Substitute that alpha what we got here. Alpha is equal to 0.02 that is a square term by the r value is a 1, and then we'll get the g is equal to, and c is equal to 1 by v z naught. Substitute the v, 0.6 into 3 into 10 to the power of 8, and the z naught is equal to 50. And we know the velocity and the wavelength, the relation is lambda is equal to v by f, or v is equal to f lambda. V is equal to f lambda. Understood, my students? R and the z, don't confuse here, under root of r and the g. And z we can substitute r c by the L. Okay. Alpha is equal to under root of r and the g, that is equal to under root of r, g is r c by the L. G is equal to, here the g is equal to r c by the L, that is equal to under root of r square c by L. G is equal to r c by the L, and it is under root of r square is there, r will get, and c by L minus c by L. And again this you can write by using the z naught also. Z naught is under root of L by C. L by C, the R, and here by the root L by C is R by Z naught. R by Z naught. This is C by L only. Or it is a R by root L by C. You can write like this. R by root LC. R by root LC is a Z naught. Okay. Then another example for the transmission line which is terminated for the normalized impedance Zn. The voltage standing wave ratio is 2 is given. Find the normalized magnitude. Normalized magnitude, the formula is there. Zn is equal to ZL by the Z naught. The standing wave ratio S is equal to, in terms of the reflection coefficient, S is equal to 1 plus the magnitude of K by the 1 minus the magnitude of K, or it is also representing the gamma is there. And similarly, the magnitude of K is equal to S plus S minus 1 by the S plus 1. The standing wave ratio is given the 2 minus 1 by the 2 plus 1. The reflection coefficient magnitude is 1 by 3. Okay. And the magnitude of K is equal to, we have the formula is there, the ZR minus Z naught by ZR plus Z naught. And the magnitude of K, the reflection coefficient, ZR by the Z naught minus 1 whole divided by ZR by Z naught plus 1. What is the ZR by Z naught? The normalized impedance, Zn minus 1 by Zn plus 1. Okay. We need the Zn, ZL plus Z naught. ZL means is a load and the Z naught is the characteristic impedance at the input side. That value is the magnitude of K is 1 by 3. Okay. So what is the Zn now? Zn is equal to 1 plus 1 by 3 whole divided by 1 minus 1 by 3. So 3 plus 1 is a 4. And here the 3 minus 1, the 2. We'll get the 2's, Zn is equal to 2. So normalized impedance is a 2. Okay. The next one, a lossless transmission line used in a TV receiver has the capacitance of 50 picofarads per meter and an inductance of 200 nano Hen per meter. Find the characteristic impedance for the section of line 10 meters long and the 500 meters long. Okay. So characteristic impedance you have to find for 10 meters and the 500 meters for the given capacitance and the inductance. Z naught is equal to, how the formula is there, Z naught is equal to root L by C, where L is at 200 nanoseconds, Hen per meter. So L is equal to 200 into 10 power minus 9 at 10 meters long. Can multiply, that is at 10. You'll get the 2000 into 10 power of minus 9, or it is a 2 power 3. So 2 into micro minus 6 Hz. And the capacitance also for the 10 meters line, we have 5 into 10 power of minus 6. Substitute to these two values, 2 into 10 power of minus 6 and 5 into 10 power of minus 10. So 2 by 5 into 10 power 4. That is a Z0 is equal to at 10 meters length. Okay, what is the value here? We got the characteristic impedance now at 10 meters line. Z0 is equal to 2 into 10 power of minus 6 and 5 into 10 power of minus 10. Z0 is equal to 63.245 ohms. And similarly, for the inductance of 500 meters line, whatever the inductance is given, multiply with the 500, you'll get 10,000 to the power of minus 9. L is equal to 10 power minus 4 N. And for the capacitance, whatever they given, the 15 to the power of minus 12, you multiply with the 500, 25,000 to the power of minus 12, the pico. And remove these three values also, then it becomes of nano, 25 nanofarads. Z0 is equal. So Z0 at the 500 meters line is root L by C, 63.2 ohms. Got it, minus 2. So with this, a completion of examples in the transmission line 1, the unit 1.